What is a black hole? Well, most people have came across the term at least once from movies, scientific talks, etc. In this video, we are trying to give you a brief idea about black hole, which is considered as a cosmic object which has always been in peak of curiosity. As the term defines, there is nothing we can see in a black hole. It would be total darkness inside. You know, reflection of light from an object make it visible. A black hole is defined as a region of space-time exhibiting such strong gravitational effects that, not even particles, and electromagnetic radiation such as light can escape from inside it. Sounds quite interesting? So, the light emitting from a black hole is pulling back with its enormous gravitational pull, making light to not escape from it, which is actually making it invisible. You may be surprised about the pictures of black hole. Actually, the objects that trap around the gravitational orbit together make large clusters around black hole, which would make it identifiable in the cosmos. The theory of general relativity predicts that a sufficiently compact mass can deform space-time to form a black hole. The boundary of the region from which no escape is possible is called the event horizon. Objects whose gravitational fields are too strong for light to escape were first considered in the 18th century. The first modern solution of general relativity that would characterize a black hole was found in 1916. Although its interpretation as a region of space from which nothing can escape was first published in 1958. Black holes were long considered a mathematical curiosity. In 1915, Albert Einstein developed his theory of general relativity, having earlier shown that gravity does influence light's motion. General relativity generalizes special relativity and Newton's law of universal gravitation, providing a unified description of gravity as a geometric property of space and time, or space-time. In particular, the curvature of spacetime is directly related to the energy and momentum of whatever matter and radiation are present. The relation is specified by the Einstein field equations, a system of partial differential equations. Only a few months later, Carl Schwarzschild found a solution to the Einstein field equations, which describes the gravitational field of a point mass and a spherical mass. A few months after Schwarzschild, Johannes Drost, a student of Hendrik Lorentz, independently gave the same solution for the point mass and wrote more extensively about its properties. This solution had a peculiar behavior at what is now called the Schwarzschild radius, where it became singular, meaning that some of the terms in the Einstein equations became infinite. The nature of this surface was not quite understood at the time. In 1924, Arthur Eddington showed that the singularity disappeared after a change of coordinates, although it took until 1933 for Georges Lemaitre to realize that this meant the singularity at the Schwarzschild radius was a non-physical coordinate singularity. Arthur Eddington did however comment on the possibility of a star with mass compressed to the Schwarzschild radius in a 1926 book, noting that Einstein's theory allows us to rule out overly large densities for visible stars, like Betelgeuse, because a star of 250 million km radius could not possibly have so high a density as the Sun. Firstly, the force of gravitation would be so great that light would be unable to escape from it, the rays falling back to the star, like a stone to the earth. Secondly, the redshift of the spectral lines would be so great, that the spectrum would be shifted out of existence. Thirdly, the mass would produce so much curvature of the space-time metric that space would close up around the star, leaving us outside. In 1958, David Finkelstein identified the Schwarzschild surface as an event horizon, a perfect unidirectional membrane, Causal influences can cross it in only one direction. This did not strictly contradict other results, but extended them to include the point of view of infalling observers. Finkelstein's solution extended the Schwarzschild solution for the future of observers falling into a black hole. A complete extension had already been found by Martin Kruskal, who was urged to publish it. These results came at the beginning of the golden age of general relativity. It was during the 1960s that theoretical work showed they were a generic prediction of general relativity. The discovery of neutron stars in 1967 sparked interest in gravitationally collapsed compact objects as a possible astrophysical reality. Black holes of stellar mass are expected to form when very massive stars collapse at the end of their life cycle. After a black hole has formed, it can continue to grow by absorbing mass from its surroundings. By absorbing other stars and merging with other black holes, supermassive black holes of millions of solar masses may form. There is general concept that supermassive black holes exist in the centers of most galaxies. At the center of a black hole, as described by general relativity, lies a gravitational singularity, a region where the space-time curvature becomes infinite. For a non-rotating black hole, this region takes the shape of a single point and, for a rotating black hole, it is smeared out to form a ring singularity that lies in the plane of rotation. In both cases, the singular region has zero volume. It can also be shown that the singular region contains all the mass of the black hole solution. The singular region can thus be thought of as having infinite density. When an object falls into a black hole, any information about the shape of the object or distribution of charge on it is evenly distributed along the horizon of the black hole and is lost to outside observers. The behavior of the horizon in this situation is a dissipative system that is closely analogous to that of a conductive stretchy membrane with friction and electrical resistance, the membrane paradigm. This is different from other field theories such as electromagnetism, which do not have any friction or resistivity at the microscopic level, because they are time reversible. Because a black hole eventually achieves a stable state with only 3 parameters, there is no way to avoid losing information about the initial conditions. The gravitational and electric fields of a black hole give very little information about what went in. Given the bizarre character of black holes, it was long questioned whether such objects could actually exist in nature or whether they were merely pathological solutions to Einstein's equations. Einstein himself wrongly thought that black holes would not form, because he held that the angular momentum of collapsing particles would stabilize their motion at some radius. This led the general relativity community to dismiss all results to the contrary for many years. However, a minority of relativists continued to contend that black holes were physical objects, and by the end of the 1960s, they had persuaded the majority of researchers in the field that there is no obstacle to the formation of an event horizon. Hawking radiation is black-body radiation that is predicted to be released by black holes, due to quantum effects near the event horizon. It is named after the physicist Stephen Hawking, who provided a theoretical argument for its existence in 1974. Hawking radiation reduces the mass and energy of black holes and is therefore also known as black hole evaporation. Because of this, black holes that do not gain mass through other means are expected to shrink and ultimately vanish. Micro-black holes are predicted to be larger emitters of radiation than larger black holes, and should shrink and dissipate faster. The Event Horizon Telescope is a project of 21st century to create a large telescope array consisting of a global network of radio telescopes and combining data from several very long baseline interferometry stations around the Earth. The aim is to observe the immediate environment of the supermassive black hole Sagittarius A star, at the center of the Milky Way, as well as the even larger black hole in the center of the supergiant elliptical galaxy Messier 87, with angular resolution comparable to the black hole's event horizon. The EHT is composed of many radio observatories or radio telescope facilities around the world to produce a high-sensitivity, high-angular resolution telescope. Through the technique of very long baseline interferometry, many independent radio antennae separated by hundreds or thousands of miles can be used in concert to create a virtual telescope with an effective diameter of the entire planet. The effort includes development and deployment of sub-millimeter dual polarization receivers, highly stable frequency standards to enable very long baseline interferometry at 230 to 450 GHz, higher bandwidth VLBI backends and recorders, as well as commissioning of new sub-millimeter VLBI sites. Each year since its first data capture in 2006, the EHT array has moved to add more observatories to its global network of radio telescopes. The first image of the Milky Way's supermassive black hole, Sagittarius A star, was expected to be produced in April 2017, but because the South Pole telescope is closed during winter, the data shipment delayed the processing to December 2017 when the shipment arrived. Data collected on hard drives are transported by airplane from the various telescopes to the MIT Haystack Observatory in Massachusetts, and the Max Planck Institute for Radio Astronomy, Bonn, Germany, where the data are cross-correlated and analyzed on a grid computer made from about 800 CPUs all connected through a 40 gigabits per second. On the 10th of April 2019, an image of a black hole in Messier 87 was published via the Event Horizon Telescope, which is very much similar to images developed from theoretical assumptions. Studies have previously tested general relativity by looking at the motions of stars and gas clouds near the edge of a black hole. However, an image of a black hole brings observations even closer to the event horizon. Relativity predicts a dark shadow-like region, caused by gravitational bending and capture of light, which matches the observed image. The image provided a test for Albert Einstein's general theory of relativity under extreme conditions. Well, there is miles to go for our scientific inventions to know deep about black hole and its singularity. We humans are evolving in space exploration in an accelerating speed. Maybe interstellar travel are necessary to avoid extinction of human species. We need to take good care of Earth to avoid forceful leaving in near future, that is millions of years before the death of solar system. Thank you for watching. More scientific videos will be uploaded soon. Please press the subscribe button and turn on notification icon to not miss anything. And please leave your comments about this video, and about your other favorite topics, as we will try to make a video on that. Help us to move forward. Thank you.